In this lecture, we will discuss bivariate normal random variables. This will be done over 3 or 4 weeks in a steady manner. It will involve a lot of computations of various kinds. And maybe by the middle end of the course, we'll understand this concept completely. But today we will start with an example. And one will have to come back to the example again to keep track of what's going on. So let me write the example down. So the example is the following. So let's say f is bivariate normal. The following happens. So x and y be two random variables with joint probability distribution function, the probability density function, given by f of xy is equal to, so I'll write this formula down in a sort of a specific manner, square root of 3 over 4 pi e to the minus 1/2, I'll have x squared minus xy plus y squared when x is between infinity and minus infinity, and so is y. So on all of R2, this is the joint PDF. So of course now I'm going to throw this at you. I'm going to say x and y are an example of bivariate normal random variables. Okay. Because now I have said this without any justification. I have not even described to you what bivariate normal random variables or defined it. But you should keep in the background that this is a motivating example. Okay. So why would I call it bivariate normal random variable? So let me try and justify that slowly, one by one. So one thing we can do is, I'd like to compute the marginal of x and the marginal of y. Okay. So let me do the marginal of x. So let me do the first computation. So the marginal density of x, let me do that computation for you. So what's the marginal density of x? That's just going to be the integral of the joint density over all possible values of y. So f sub x at the point x is going to be the integral from minus infinity to infinity of f. I integrate out y completely. Right? This is what the marginal is going to be. And what is that going to be equal to now? That's going to be equal to the integral from minus infinity to infinity dy, and let me just cut and paste the density function. So I have the density function, copy, I place that here, so let me place that below, and then maybe move across, place this across, make all the y's orange, and all the x remains constant, right? That's what's going to be like. So then I'll move this up again. This is what I have to find. So now again I'll remove all the white outside. So it's root 3, 4 pi outside. I have e to the minus 1/2 x squared inside. And then I have the integral from minus infinity to infinity. I have this whole quantity right here. Of course, I've taken out some people, so I'll just have to take them out. So I'll remove this guy here and I'll move across here. This is what I have. Right? Now x is fixed and only y is changing. Right? That's what I would do. So this is something one can. You should just think a little bit. So what will this be? If I complete the square, it will just be y minus x by 2 the whole square. Right? So this looks like. So let me just write this down. So this looks like, so minus xy. So this is a fact right here, minus of x comma y plus y squared, right? This is the same as y minus x by 2 the whole square, and then I have an x by 2 the whole squared added, so I have to subtract minus x squared by 4. And that's exactly what this looks like. There's really no other answer to this, right? So now that's going to be, so then if I use this fact here, so what will I get? the above is equal to, so I'll copy this whole person right here, copy it right here. So the outside guy remains the same, right? So this guy remains the same. That's x squared out here. This person right here, I'm going to split up into two parts, right? Y minus this and so on. So let me just do that. Let me go and do it. Let me write this inside as, so minus 1/2 y minus x by 2. That's a constant, the whole squared. And outside I'll have a minus x squared by 4. And a minus will become a plus right here. Because I have this minus sign. So it'll minus of this whole thing, and then that will give me it will become a plus. Very good. That's what I have. So I'll use this fact. So using, this is what I have. What is this going to be now? This is going to be equal to, so I'll write the root 3 by 4 pi e to the minus. This will be 4 minus 4 minus 2 minus 3 by 8 x squared. I'll have this. It's very good. Now my claim is that, this is a claim that I'll make, that small exercise, that the first part is algebra. The second part of the claim is that this guy is going to be just root 2 pi. So why is that? That's because of the following fact. Something will check that this person right here, because x is fixed, right? X is fixed, right? This person is going to be equal to square root 2 pi. So let me write this down. So maybe a better way of writing it is the following. This, I'll copy it. If I place it here, so this is equal to this. So why is that? You think a little bit. The reason is that this is just a normal density with mean x by 2. So that means it integrates out to 1, but the density constant is missing. That's why it's going to be root 2 pi on one side. That's what. So then if I do this calculation correctly, so I will get f sub x of x, if I do the algebra fine, is going to be, if I finish the calculation, it will be root 3 by 4 into 1 over root 2 pi. I'll have e to the minus 3 by 8 x squared. Minus infinity less than x less than infinity. So it means if x and y have the joint density given above, then x is normal with mean 0 and variance 4/3. That's what we get. Now let's do a little bit of a calculation. Let me just get something here. Just get this. So now if you look at this calculation right here, so I start off with this thing and I end up getting y is this. Let me move it down so you can see the right. So now if x and y were given by this, then the marginal of x is going to be normal 0 by the calculation. That's why the name bivariate, but there's more justification. See, this is symmetric in x and y, right? If we change x and y, this function will not change at all. If you change x to y and y to x, it will be the same. So symmetric. That means even y has the same density of this calculation. So let's write that down. So something you have to just check a little bit. So I'll leave the exercise. You can check f of xy is equal to f of y comma x, because I've changed the rules back, for all x and y between infinity and minus infinity. So this implies that the joint density of y, it's also will be the same, because I'll replace the roles of y and x, I'll get the same answer. So root 3 by 4, 1 over root 2 pi, e to the minus 3 by 8 x squared. So therefore, y also is normal with mean 0 and variance 4/3. Okay. Very cool. So now let me just make it double again, so I can show both sides to you. Make the window twice. Oh no, I don't want this. Cross here. Very good. Let me show this to you. So what have we established? We established if x and y have this joint density, then y is normal and x is normal as well. Right? So that's the motivation for giving the name bivariate normal. Of course, there's a far more justification, but I have two random variables x and y. So two random x and y whose individual marginals are normal, and they have a joint density, which is not a plot of the two densities. Okay, they're a little different. So I guess I made a mistake here. It should be y squared. Sorry for that. Y squared, and between y between infinity less than y less than infinity. Very nice. So now this. So we also notice the following fact, and also note the following fact that fx of x times fy of y is not equal to f of xy. So therefore, x and y are not independent. So I've given you an example of a joint density of random variables where the marginals are normal. Right? That's very nice. So now I like to sort of just play with a little bit, try to understand how the conditional density looks like, right? If y given x equal to x, right? So let's do the next step. So we have finished the marginal densities. Let's do the conditional density of y given x equal to x. So let me try and do that for you. So I've shown you again that x and y are marginally normal. That is, and they're not independent because fx times fy is not f of xy. Very good. Now let me come here. So how do I find the density? So we know that f of y given x equal to x at the point y is just going to be equal to f at x comma y divided by f sub x at x. So our convention, let's just color it so that we're clear about this. So all the y's are orange. Let's do all the y's orange. So this is orange. So x is fixed. I'm trying to find the density of y. So it's a y given x equal to x. So x is fixed, y is between minus infinity less than y less than infinity. Very good. So how do I compute this now? This is quite easy, right? Because I know joint density. This is equal to what now? So f of xy we know. Let's go back up. F of xy somewhere here. Exactly this guy. So f of xy is exactly this guy. It's going to be this guy. I copy it. I come down here. I plug in f of xy. This is true for any x in the real line and any y in the real line. That's exactly that. And I have to divide this by f sub x of x. What is that? That's given by this answer right here. So I take this person right here, I grab this, they're all non-zero, so I can always divide. So I divide by this number. This is true for all y between infinity and minus infinity. Now if I do the algebra correctly, how will I get? If I do the algebra correctly, what should I get? If I cancel everything properly, if I use the algebra, I get e to the minus. So the x squareds will cancel off in some way, and I'll get e to the minus y minus x by 2 whole squared, and I'll have 1 over root 2 pi. The root 3 over 4 cancel is quite clear, and all I'll get is this guy. Very cool. So that means what? Let's stare at it a little bit. So we have shown that the marginal of y, conditional density of y given x equal to x is given by this formula right here. But what does it look like? This looks like a normal density with mean x by 2 and variance 1. Right? Or it's 1/2 here, I'm sorry, 1/2 I forgot. 1 by 2, I forgot. So that's the kind of a nice observation we have, right? So that means y given x equal to x. So y given x equal to x. Let's add in y in our convention is given by a normal distribution. The mean is x by 2, and the variance is 1. Kind of nice. So that means it's kind of nice, right? So as x gets larger and larger, the mean gets larger and larger, but the variance stays 1. And that's kind of a nice idea of this whole random variable. So as x changes, the mean of y also changes. Mean of y given x equal to x changes to x by 2. So this is the first example we have done of bivariate normal. So what I will do next is I will start from here. So you should keep this example always in mind when understanding bivariate normal. So this is an example of a density in which the joint density is given by, joint density, this is the wrong look. We go here. The joint density is given by this, right? And then we compute the marginal density of x to be normal, 0, 1, 0, 0, 4 by 3. By symmetry, y also was normal 4 by 3. They were not independent. And the density of y given x equal to x turned out to be normal x by 2, 1. So there's some relationship between y and x that forces the joint density to be of this form, and individuals being normal and even conditionals being normal. Right? So this is something that we will have to utilize as we go along. So such distributions are called bivariate normal when the marginals are normal, but not quite, but I have to write the correct expression for you. So let me write it down. Let me see if I can make a density formula for you. Let me just do that. So it'll be a little bit messy, but we'll try and write this down now. So here's the definition. So here's the definition. So let me write it in pink, and I'll close for this session. So x and y are bivariate normal. So you remember normal had parameters like 0, mean and variance, mu and sigma squared. This will have 4 parameters, in fact 5 in fact. So mu1 being the mean of the first one, second one, sigma 1 squared, sigma 2 squared, and then how the interdependence happens. That's given by rho. So this corresponds to the x part, y part, x part, y part, and the dependency between x and y. Right? This happens if it has a joint PDF. The joint PDF is a little bit messy, given by. So I will explain the terms as I go along in the classroom slowly. Given by f of y, f of let's say x comma y is equal to, so I'll have at the bottom I'll have a 1 divided by 2 pi. I'll have both the variances, sigma 1, sigma 2, square root of 1 minus rho squared. I'll explain what rho is in a second. And inside I'll have this times, I'll have exponent of, so I'll have minus 2, 1/2, 1 minus rho squared I'll have, and then the first term will look like how y behaves, so it will be how x behaves. So x is normal with mean mu1 and variance sigma 1. And the next term is how y behaves, that's y minus mu2 divided by sigma 2 squared, plus you'll have the cross terms, so that will be minus 2 rho into x minus mu1 by sigma 1 into y minus mu2 by sigma 2. So that's how the joint density will look like. So let me make it all nice and fancy for you guys. So there's this, and let me make it a little bit smaller. So it's I'll resize this, make it a little bit smaller. So it goes here. I'll make this a little bit smaller as well, not too small, so you can read it. So it comes here and then move across. So this times this is the joint density of x and y. Okay. So I have to explain several of the terms to you. So this is true for when minus x is less than minus infinity, and even so is y is less than infinity. So what are the terms here? The terms are, it will turn out, so this is just a, as of now, this is just expression, because I'm just saying x and y are bivariate normal with these parameters. That's all I'm saying, nothing else, right? So what are how does one do this? So you can justify later on, we will see this fact that that so this you have to assume two things. You have to assume rho is not equal to 1 or minus 1. Okay, that's it. So what we'll see later on is that mu1 is Ex, the mean of X. Sigma 1 squared is the variance of X. Mu2 is the mean of Y. Sigma 2 squared is the variance of Y. And then rho is in fact the correlation coefficient of X and Y. That's just saying it's just the covariance of X, Y divided by the square root of the variance of X times the square root of variance of Y. That's what rho is. So this we will see later on as the course progresses. So as of now, the joint density means, it's bivariate normal means it has this joint density. So one can go to the example that we did before, and let me just check that. Let me see if I can find that for you. Let's see if I can get that. Very nice. Let me go back here. Okay, I have to do this. Okay, I have to get this double for you so I can see both the windows at the same time. Let me see if I get that. Very nice. Okay. So one can check that this person right here has the same form as this for some values of rho, sigma 1, sigma 2, and mu1, mu2. I'll let you check that. It's not hard. So you can check, for example, the example. Yeah, from this idea you can check mu1 is 0, mu2 is also 0, sigma 1 squared is this, sigma 2 squared is this. You can try and compute rho. It's quite nice. So exercises that we come back here is that one can compute mu1, mu2, sigma 1 squared, sigma 2 squared, and rho for the example. That also we will see later on, but you can think about how to do that yourself. Okay, we'll stop here.